Okay, so we're going to take a look at some properties of integrals that you're going to have to memorize and use throughout. So the first one is on positive and negative areas. And so I just want to explain how when you're finding the integral of a function, the area above the x-axis is positive and the area below the x-axis is negative. And so the reason why is, remember how when we defined the integral, we defined it as a Riemann sum, and so we had our rectangles, and so but remember that the height of the rectangles was given by the value of the function at the different points. And so if you find the area of these rectangles above the x-axis, the y value is going to be positive. But notice that if you go down here, for example, let's say I take this rectangle right here, the y value right there is going to be negative. So when you multiply the width, which is delta x, times the height is going to be a negative number. And so this area down here is going to be counted as negative. Okay, so the second property is what happens when you you're multiplying a constant times a function. And so here you have an example. This is your function. And the area of this first triangle right here is the base is 10, the height is 1, 2, 3, 4 divided by 2, so the area of this is 20. And so notice that this triangle that's twice as big, so it's multiplied by the constant 2, the area of that is 40. So basically what this says is that you can take the constant out of the integral and just find the integral of the function and then multiply it by the constant in the end. And so that's it. And so here we have an example of two functions, f of x and g of x. And so the question is, what's the integral from a to b of the sum of two functions, f of x and g of x? And so this function right up here, this is the sum function. And notice that if you find the area underneath the curve of the sum, it's going to simply equal to the area underneath g of x plus the area underneath f of x. So that basically says just the same as for derivatives. When if you're getting the integral of the sum, it equals to the sum of the integrals. So you can find the integral of f of x plus the integral of g of x. And it works similarly for the difference. If you have the integral from a to b of a difference, f of x minus g of x. Here we have an example, a graphic example of f of x minus g of x. If you take the area underneath f of x and then subtract the area underneath g of x, you're going to get exactly the same thing. So the same way as for the sum, you can split up the difference. Sorry, dx. Let me erase this little extra parentheses, and then minus the integral from a to b of g of x. So just like for the sum, you can separate the difference. Okay, now this is an important one. Here we have a interval, and we're gonna break it up. Now let me pose this question: what happens if you add the integral from a to b of f of x plus the integral from b to c of f of x? So in other words, if you find the area under the curve from a to b, so then you would get that's this one right here. And then you find the area underneath the curve from b to c, you would get this one. Well, obviously this is equal to the integral from a to c of f of x. So this basically means that you can, if you have a line and you want to split up the integral, you can split it up wherever you want, as long as you don't have any gap in between. So that's a really good property that we're going to use a lot. Okay, now let's take a look at this. One's a little trickier to see, and so the question I have for you is the integral from a to b of f of x dx the same as the integral from b to a of f of x dx? So basically, well, the answer should be no, right? But, well, maybe you can answer almost. Almost. Okay, so remember that in the formula you had delta x is equal to b minus a over n. And so if you switch from b minus a over n to a minus b over n, if you just flip those, well, what's going to change? Well, the number isn't going to change, but these two are going to have opposite signs. And so since they're going to have opposite signs, so this means that you can flip the limits of integration if you want, but you have to make one of them, you have to make it negative whenever you flip the limits of integration. And that one we're going to use quite a bit as well. So those are all the properties that you need to know. And so write them down, commit them to memory, and that way you can have them on call whenever you want them.